Although psychology and statistics seem like separate entities, each operating and governing their own land, minding their own business, they're actually intertwined on a fundamental level. The peculiar combination of psychology and statistics is seen in a wide array of areas such as population data, game shows, and degenerate Dan down at the local casino. Many of the statistical problems that baffle us and seem counterintuitive do so because of our way of thinking about the problem, because our psychology is sometimes tricking us into approaching a problem in a not so rational way. This video is the second of a 5-part series about psychology and statistics, but just like Black Mirror, they can all be watched independently. You wake up to find yourself on a game show. The game show host Bob shows you 3 identical doors. Behind 2 of them he tells you they are goats. And behind the last door is a brand new Lamborghini Revuelto 2024. Whichever door you keep in the end, you'll receive what's behind it. Bob knows what's behind the 3 doors and asks you which door you would like. Well, you think to yourself, all psychology tricks aside, it's a 1 in 3 chance either way, so you pick the first door. Instead of opening the door, Bob goes to open another of the 2 doors not picked, revealing a goat. He then asks you, would you like to switch to door number 3 or stay at door number 1? The answer seems obvious at first. It doesn't really matter. There are 2 doors, the Lambo is behind one of them, so it's a 50-50. But a closer look reveals that your odds of winning are actually 1 in 1/3 chance if you stay with the original door and 2/3 if you switch. But how can that be possible? When you initially pick a door, there's a 1/3 chance that you got it right, thus meaning that there's also a 2/3 chance that you didn't get it right. This means that when Bob opens a door revealing a goat, the probability of you getting it wrong the first time is still the same. The 1 in 3 stays locked. And this means that after Bob eliminates door number 2, there's a 2 in 3 chance that the Lambo has to be behind door number 3. The trick here is that Bob knows where the car is, and he will never knowingly open a door leading to the car. He's always going to reveal a goat. Think of it like this. Bob offers you the choice between one door or the 2 other doors. A second way of seeing this problem is visualizing all the different possible games. Suppose we want to look at all the different kinds of games possible when you pick door number 1 and stay with it. The first game looks like this. The car is behind door number 1 and goats behind door number 2 and 3. You pick door number 1 and Bob reveals a goat behind door number 2. You decide to stay, he opens the door and you win. Wow! In the second game, the car is now behind door number 2. You again pick door number 1, the game show host opens door number 3, revealing a goat. You stay and end up losing. In the third and last possible game, around door number 1, the car is now behind door number 3. You again pick door number 1, the game show host opens door number 2, revealing a goat. You stay and end up losing. As you will see, you end up losing 2 out of 3 times if you stay. Thus meaning if you switch every time, you would have instead ended up winning 2 out of 3 times. If you're still not convinced, imagine 100 doors. Behind 99 of them, goats, and behind 1 of them is the car. You pick door number 1, and because Bob can only open doors leading to goats, he opens 98 doors and offers you to switch. Now the choice is between your original door and the last door that Bob didn't open. Initially, there was a 99% chance that you didn't get it right, and after he opens 98 of the remaining doors, that probability stays the same, meaning you have a 99% chance of winning if you switch. Now imagine the same case, but with 10 doors only. You pick door number 1, Bob opens 8 of the doors and offers you to switch. So if the same applies for 100 doors and 10 doors, why wouldn't it apply if there was only 3? If you're really still not convinced, you can try out a Monty Hall problem simulator. Try to run it 1,000 times, and it should always follow a ratio of about 67% wins if you switch and 33 if you stay. And if you still don't understand the problem, it's okay. This problem is perhaps the single most controversial and debated problem in probability theory. It became popularized after a reader sent in the case as a question in Marilyn Savant's Ask Marilyn column in Parade magazine. Here, she argued that the probability of winning if switching was in fact 2/3, in response receiving a massive influx of angry people, including 1,000 academics holding PhDs, all calling her wrong. Scott Smith, PhD from University of Florida, wrote, "You blew it and you blew it big. There's enough mathematical illiteracy in this country and we don't need the world's highest IQ propagating more. Shame." While Charles Reed, PhD of the same university, urged her to obtain a standard textbook before she would answer such a question again. It was only after a strong encouragement to make experiments and simulations that the public opinion started to turn. A big number of readers, initially not convinced, were in awe after performing the experiment with their students and colleagues, and in fact winning 66.7% of the time that they were switching. So a big shout out to Marilyn Savant for sticking up to her own ability while criticism rained down from all sides. And a big thanks to Erik Kampmann at Copenhagen Business School for inspiring this video.